Hello, everybody, and welcome to the latest session between Pangea and AI Accelerator Institute. It's great to have you all joining. I'm going to wait just a few seconds while folks are coming into the room, but thank you for tuning in wherever you are, whether it's morning, afternoon, evening. It's great to have you joining us. We're going to be joined by Sourabh Satish today, who is the co-founder and CTO at Pangea. Today's session is going to be around building and securing AI agents, a tech leader crash course. Super session today from Sourabh, which is going to cover demos of MPC configuration, an overview of existing security guardrails from open source projects and cloud service provider offerings, all the way through to commercial tools and DIY approaches. Carry on with a comparison of pros and cons across various guardrail solutions, and then finally, actionable best practices for implementing those guardrails that will secure AI agents without slowing down your innovation. It's going to be awesome to have Sourabh leading the presentation today. If you guys have any questions whilst you're watching, drop them in the chat on the right-hand side. Sourabh and I will be delivering a Q&A session in about an hour's time. So drop those questions in there and we'll get to them at the end of the session. Thanks for tuning in. Sourabh, I'm going to hand straight over and here we go. We'll join you folks in an hour for Q&A.
Hello, everyone. My name is Sourabh. I'm CTO and co-founder for Pangea, and I'm here to talk about building and securing AI agents. Hopefully, this is going to be a fun session with some hands-on look at code of writing an AI agent. So in terms of agenda, I'll just briefly cover some generative AI concepts, especially as it relates to enterprise AI architectures. That is relevant to this discussion. We look at some code of building a basic AI agent and how MCP changes the implementation of an AI agent. And then we look at basic agent security issues, especially in relationship to how MCPs are being used by the agents. And then we'll talk about security solutions, guardrails, open source, commercial, engineering and security best practices. And then we'll end the session with a brief look at Pangea's guardrails that are available. All right, so hopefully most of these concepts are nothing new, but nonetheless, probably important to recap in the context of this discussion. As you all know, LLMs are basically a mathematical representation of all the information on that it has been trained. But LLMs are really trained on the data at till a particular point in time. That means that LLMs really don't have any access to real-time information, things like stock price, current news, weather, etc. And when we talk about LLMs, we are really referring to foundation models, which are really large models trained on a vast amount of data. Whereas small language models or domain language models are models which are smaller and really trained on a subset of data pertaining to a special topic on which we really want the LLM to excel and not get conflated or confused about information from all kinds of sources of information. Context window is really the working memory of an LLM, which allows the LLM to analyze more, take into account more and more data as it tries to predict the next set of tokens or answer a user's question. The bigger the memory, the more it can look back and respond. And this is what really enables the LLM-based application to have a conversational experience. Prompts are really constructed to communicate various forms of input to the LLM to achieve the desired outcome. And in order to do so, there are ways in which the data is communicated to the LLM. They are really communicated on behalf of certain roles. So a system role really is meant to facilitate communicating from an application developer or administrator's perspective as to what the AI application should be doing, how it should be doing, and so on and so forth. And then the user role really captures the input that is given by the user to the application that is then passed on to the LLM. Context is really the data that is associated with along with the user's question in order to make the LLM take that information into account in order to come up with the answers. And then the assistant role really represents the answers that are given back by the LLM. And then tools is yet another role that has been recently added in order for the AI applications to communicate a set of capabilities that it has that makes it capable of interacting with other sources of information that can be, or things it can do in order to, generate more relevant data that can be passed back to the LLM for it to respond to the user question. AI apps and agents basically use LLMs to process the input data and get the relevant output. LLMs by themselves cannot really execute any tools and actions. You might often hear LLMs calling tools. That's really a short way of communicating the fact that LLMs can guide the agents to call the tools. So again, very important point. LLMs by themselves have no capability of interacting with the external environment or calling tools. They really are used to guide an agent or an AI application to do whatever is needed in order to extract information that can be incorporated into input to the LLM for it to do its task. Now, in case of enterprises, the important thing is that in order to answer the user's question, relevant data from enterprise applications and data stores have to be passed into the LLM for a particular enterprise use case. In case of enterprises, this data could be locked in enterprise applications or data stores like Google Drive, etc. In most of in the most common architecture for in production AI applications and enterprises is all about retrieving this data and storing it into a data store in a format that makes it and that is very efficient for retrieval, so that the relevant piece of information can be passed as context to the LLM for it to then come back with a response. So retrieval augmented generation is really the term given to this kind of capability where where the data is retrieved from other data sources and augmented to the user question as an input to the LLM to generate an answer. And very often, it's stored in a vector DB, which is nothing but a specialized database for efficient information retrieval. Agentic RAG is kind of an evolution of a RAG architecture, which uses vector DB, wherein an agent can be used to interact with its environment to retrieve the relevant piece of information for the user's question, rather than just retrieving it from a vector DB. Now, AI agents can interact with the external environment and services and applications, but they can also interact with a vector DB, which can again be the source of information. So it's not necessary that the agents are connecting with other applications. They could simply be connecting to a database to retrieve the information. Nonetheless, agentic RAG just are more real time and are able to retrieve information from many other applications that the agent could be connected to. Agentic workflow really is the whole process of orchestration, collaboration with the ability, the whole process of orchestration and collaboration to, answer a user's question. In a typical AI workflow, a user's question is really given to an AI for it to then generate the response on the basis of the information that is provided to the AI by virtue of the input or the information that the AI model itself has. Whereas in case of an agentic workflow, there is a much more well orchestrated way of answering the user's question, where a user's question is augmented with a way to solve the problem and the capabilities that the agent can have, such that the LLM can break down the user's question into a plan, and as part of multiple steps of a plan, the LLM can guide the AI agent on what actions and tools to execute in order to retrieve the answer for the step, and then incorporate that information into its plan and decide what is the next course of action, and repeat this loop till it has either retrieved the right answer or has no more actions to execute, and then that result is given back to the user. Now, this interaction with the environment that I've been saying is done on behalf of tools, could also be done by collaborating with other AI agents. So it's not just about executing tools on behalf of an AI agent. It could be also about collaborating with other AI agents which have been purpose built for a particular use case. Now, as you might have realized, AI agents are nothing but software programs which basically have an ability to interact with the environment. So in terms of components, AI agents really have four components. The first one is its ability to interact with the LLM, where it does things like reasoning and planning and breaking down the problem into subtasks and figuring out how to come up with the right answer by invoking the right or executing the right steps. Uh, prompts are prompts are a component where an AI agent guides the LLM on how to solve the problem, exposes what kind of capabilities it has so that the LLM can invoke the right or guide the agent to invoke the right tools for the steps. Then the agents can optionally also have short-term and long-term memory, where it can cache or store historical information, other piece of information, from the current conversation, past conversations, etc., so that it can more efficiently respond to certain pieces of the question rather than invoking the tools all the time. So it kind of is an ability to cache the results of the tool calling or have more data that it can use in order to provide the right kind of context to the user's question so that the answers can be more efficiently responded to. And lastly, the agents really are the pieces of code that implement or call the tools, not the LLMs. So the tool implementation, tool calling is kind of part of the agent functionality. So let's look at really how a basic agent works. When a user's input comes in, the agent really communicates, to the agent system prompt, which basically guides the agent on how to solve the problem. And in order to solve the problem, the agent exposes the set of capabilities it has in order to assist with that problem solving via exposing these capabilities as tools to the LLM, and then the user prompt. Now, what is really interesting here is that the tools have kind of have a description, have what are its input parameters, what's the format of the input, and how it is going to produce the answer. And so the real key aspect here is the tool description. The tool description has to be detailed enough, complete enough, so that the LM can recognize that this is the right tool to call for this particular step in the plan for it to answer the user question. And so when the user's question along with the system prompt and tool is given to the LLM can identify the plan, and for the steps of the plan, identify which tool, what input to the tools needs to be sent over to the agent. The agent then executes a tool, identifies the results of the tools, gives it back to the LLM along with all the history, and then the LLM can decide what more tools to call as part of its plan, or whether this is the end of executing all the tools and it has the right final answer, and then it packages the right final answer back to the user, and the agent ends up responding to the user or the caller of the agent. So this is really the basics of an AI agent. And in order to make it all real, let's really look at code. So I have a sample agent that I've written in Python. It uses no frameworks because I really didn't want to. I really wanted to understand how it works at its core and not be able to see what's going on by virtue of using some libraries or frameworks. Again, the most important part is the system prompt, which I'm showing here on the right. And as you can see here, the agent kind of declares to the LLM that, hey, this is my purpose. These are my capabilities. So here I have a calculator capability, I have a response time capability, and the description tells what these capabilities are. And then I guide the LLM on how to kind of answer a user's question. So given a user question, it needs to be able to, properly break down the problem into sub steps and be able to use any of the available capabilities that the agent has in order to extract the input, which can then be in order to perform the action, whose results are then going to be sent back to the LLM as an observation. The LLM should take into account the user's question, the multiple steps that it has to execute, the results of individual steps in order to decide what to do next, which could be about executing more actions or maybe compiling the results of the called actions as results and giving the final answer back to the user. So this is the system prompt. And the more important piece is that the ability for it to interact with the environment is declared to the LLM as a set of tools. So let's look at code. So I'm going to go into my agent code. And this is really the most interesting piece of the entire agent code. I have an agent.py file, which is pretty much the entirety of the implementation of the agent. And the tools that the agent can declare to the LLM are implemented in tools.py file. I've just faked the response time tool, which returns a random number, and the calculator just basically calls an eval on the input. And so from the main interesting functionality of the agent, here's what is going on. When the user gives an input, it along with the system prompt is sent as an input to the LLM. The LLM responds back with a plan and the action to execute on behalf of the first step of the plan. If the results of the LLM doesn't have any action, it means that the LLM is done and there is nothing more to be done. But if there is an action and an action input, it really is about the agent then invoking the action, extracting the results, and passing the results back as the subsequent input to the LLM. The LLM can then take the results into account in order to decide what the next set of action is, or it's done executing all the actions and here's the final answer. So this is how simple the agent is. And now just let's run the agent and see it in action. So here I'm going to just run the agent. So you can see that. So here it says, I'm your helpful AI agent. How can I help you? I'm just going to ask it a question. What is the response time of abc.com? So let's see what the agent does in the whole code as it executes. So the first loop, it takes a user input and comes up with a thought that in order to respond to this question, I really need to invoke the response time tool. Now it's able to identify that response time is the tool to call because it kind of is able to interpret on the basis of the tool description that it is the right tool for the step that needs to be executed for answering the user's question. So it responds back with, hey, this is the action to call. And it forms the input as expected by the action by virtue of the tool description and gives it back to the agent. Agent then identifies that, hey, this is the tool that I need to call. Yes, it is one of the tools that I have. Here's the input. It invokes tool, retrieves the results, and passes it back to the LLM as an observation. The LLM then takes that observation into account, the entire history of the conversation, which is a system prompt, the first question, the plan, the steps, etc., and then says that, hey, the response time for the website abc.com is 51 milliseconds. There's nothing more to be done because that was the question that was asked. So I have no more actions to call upon. And this should be really the answer that is returned to the user. So now let's look at a little more, interesting question that we can ask. So what is the sum of response times of abc.com and cde.com? So here, hopefully the LLM recognizes that there are multiple steps for answering the user questions, which is invoking the response time tool and invoking the calculator tool in order to finally respond. So let's see how the application does or the agent does. So here, in order to answer this question. It really looks at the question, the history of question answer that have occurred in the past, and it comes up with a plan and says that, hey, I already see the response time for abc.com in my memory, so I really don't need to invoke any actions for retrieving response time for abc.com, but I don't know anything about cd.com. So let me tell the agent to invoke the response time tool to retrieve the response time of cd.com, which the agent gladly, responds with, which then is taken into account by the agent as an observation. And now the agent says, well, now I have the response time of cd.com, and all I need to do is sum that up by invoking the calculator tool. So it passes on the right, calls upon the agent to invoke the calculator tool with the input of the two response times. The agent then gladly answers and executes the calculator tool, gives the result back as an observation to the LLM, and the LLM is able to identify that, hey, I have the final answer. There is no more actions to be executed. So here's the final answer that needs to be given back to the user. So you can see how the LLM was guided by the system prompt on how to solve the user's problem, was able to identify the capabilities that the agent exposes to the LLM, guide the agent to execute the right set of tools, incorporate its results, and was able to finally come up with the answer that the user was looking for. So this is really, how the AI agents work in the most simplest form. So let's get back into the slides and continue talking about, what this AI agent architecture was, what are the pros and cons, and how does MCP changes anything. So what you might have observed is that what you saw was a very coupled architecture. The tool, the system prompt, all was kind of in the agent code. It also required me to be an expert on all of these external services that I'm interfacing with, and be able to call the right API, be able to take the results, package them as appropriate results that can be sent back to the LLM, and so on and so forth. And the tool implementation, because it was literally as code within the agent, the only way for me to share this tool implementation with other agent authors is by code, which is really not a great way to share, shared implementations. So MCP, which really is more about the way context is packaged to be sent to the LLM. For me as an application developer, yes, the protocol and the structured way of sending data back and forth between the LLM is important, but more importantly, it helps me think about the AI agent in more modular way, where now the application can have not have to hard code the tool implementation within the agent, but can be moved out into an external component that can be shared by multiple agents. It can be maintained independent of the agent code, and makes my life as an AI agent a developer really simple. I've delegated the implementation of the MCP server and the tools to the expert on that particular service. They can maintain it, and I can just simply consume their capabilities as part of my agent code. So an MCP-based application is really made up of three components. There's a host application, which is housing the client code that can talk to the MCP server, retrieve the tools that it can pass on to the LLM as the set of capabilities that it has. And then when the LLM tells which tool to call, the client can basically interface with the server to call the tool on the server, and the server can give back the results. So the entire tool description, tool implementation, all that is kind of on the MCP server, and the agent is simply interfacing with the MCP server to execute the tools and call the tools. MCP server really has three pieces. It has a tool implementation. It also has an ability to expose resources back to the agent, or facilitate any kind of persistent store that might be needed across multiple tool invocations. And it also can have prompt templates, which really exposes how to really invoke the right set of tools, and pass in and retrieve the results out of the tool invocations, because the expert of the particular service knows how to take the input and output out of their services, as it is interfacing with the LLMs. So what really changes in the basic AI architecture, agent architecture that we have looked? Here you can see that all that has happened is instead of having the tools hard-coded within the agent, its implementation has moved out of the agent into the MCP server. So now when the user prompt comes in, the agent can connect to one or more MCP servers, retrieve its tools, and then expose those tools as capabilities to the LLM along with the user question so that the LLM can, again, the role of the LLM doesn't really change. It again comes back with the plan, the tool input parameters, and so on and so forth to the agent. And now the agent, instead of invoking the tools locally, it can then call upon the MCP server to invoke the tool, get back the results, package the results back into the input to the LLM, and let the LLM do its job of executing the plan till it has the final answer. So from the interaction of the agent with the LLM, nothing much has changed. Just the agent has become simpler in terms of not having to implement the tools, but just having to interface with the MCP server to retrieve the tools and call the tools. So here, from a code perspective, instead of passing and hard coding the tools within the system prompt, now the AI agent can dynamically create the system prompt by connecting to MCP servers, enumerating their capabilities, incorporating that into the system prompt, and sending it to the LLM. That's all that has changed. Instead of hard coding, you're dynamically building the system prompt. And the beauty of this integration is because MCP server is external, because the agent connects to the MCP server, if the MCP server evolves, they might introduce more tools, change the implementation because the interfaces are changing of the dependent service and so on and so forth. All of that is on the MCP server side. The AI agent can automatically evolve by virtue of new tools that might be exposed by the MCP server that it connects to, and become and can evolve a set of capabilities that it declares to the LLM. So the exciting piece is that if the service introduces new functionality that is exposed as a new tool, nothing changes on the AI agent. It dynamically can expose this new capability to the LLM for it to be able to solve more interesting problems than it could in the past. The other interesting nuance over here is because LLMs are so good at, processing unstructured data, producing data in the required format. MCP servers are expecting the action input to come in JSON format because they're really implementing this as JSON RPC. I can tell the LLM to structure the input to the action as a JSON object, and LLM will gladly comply and give me back the action input in the expected format, and that I can seamlessly pass to the MCP server when requesting it to invoke a tool, and so that the interaction can continue on. Those are the kind of things that have that change in an AI agent architecture in light of MCP. So now let's look at the security risks of an AI agent. As you might have realized, AI agents are really meant to serve the needs of a diverse kind of users within an enterprise. So, and different users within enterprise could belong to different roles, can have different kinds of privileges, authorizations on various systems, etc. Whereas the agents are serving the needs of many users. So by definition, the agents have more capability than a variety of users within an enterprise that are calling upon the agent. So when a user is interacting with an agent, users may be able to trick the LLM or trick the agent or guide the agent to perform actions that they were not otherwise authorized, unless the agent is really taking the user, authorization into account when invoking the tools. So unless the AI agents have been designed correctly, there is a possibility that the user may be able to tell the agent or guide the agent to perform elevated actions, privileged actions that they themselves did not have access to. And then because the agents are processing input, whether it is user input or data that has been collected on behalf of the action results from external systems, etc., as long as there is external data involved, there is room for malicious or foul play where the input data can be constructed in malicious ways to cause the agent to misbehave. We'll dig deeper into what this misbehavior really is. But unless the input data is analyzed properly, cleansed properly, there is risk of causing the agent to misbehave by virtue of making it do unexpected things. Now, because the agents are interacting with external systems, in order to interact, with protected systems and services, there are access tokens and credentials involved. If the agents are not properly managing these credentials in services like Vault, there is room for accidental leakage of credentials by virtue of source code, and so on and so forth on behalf of the agent. Then, as we talked about, a capability called memory that is part of an agent design. There is risk of that memory being exploited to retrieve information on privileged questions or entities that the user did not have access to. So what I mean by that is, let's say, the response time was being questioned about two sites, abc.com and cd.com. And maybe the user did not have access to the response time of abc.com. But if the agent ends up recording the response time of abc.com, and when a user who did not have access to query the response time of abc.com asks a question, and if the agent just leverages the memory instead of trying to execute the tool, it could potentially answer the question about abc.com, which the user did not have privilege to, and thereby the memory can serve answer to questions about privileged resources that the user could not have accessed in the past. So when designing the memory of an agent, what to record, what to cache, what to use as context to the LLM, one has to keep into account what kind of isolation mechanisms have to be put in place when it comes to multi-user scenarios, interfacing with other external systems which have different levels of privileges for different kinds of users. And lastly, because agents are invoking these tools, which are invoking functionality on top of other external services, because this is machine code, if the agents go have a bug or runaway loops, etc., they can really stress the external systems by more than necessary tool invocation or API invocation on top of these services, thereby causing these services to become unresponsive or overloaded, causing denial of service not just for agent, but on these services that had other purpose within the enterprise. And not to mention resource abuse, where it can cause overusage of tokens on top of LLMs or resources on these services, making them inaccessible for valid use cases. MCP by themselves, expose and add on other risks. And as I've mentioned, MCP servers think of them as simply as wrapping the endpoints on these external services as tools exposed back to the LLMs. MCP servers really can be used in two ways. One is you can literally run the MCP server locally as a mechanism to invoke the endpoint that you were going to otherwise invoke directly within the agent code. But MCP is just giving you a level of abstraction to these endpoints. All these MCP servers can be hosted as a web service shared that can be shared across multiple agents. Now, when these are exposed as a shared service, you have to make sure that they are properly authenticated, proper authorization checks are performed so that different users of this MCP server can be properly authenticated and authorized to invoke the tools that are exposed by these MCP servers. So authentication authorization becomes the first level of security risk on top of an MCP server. And then, these MCP servers, depending on who's writing them, where you're getting them from, these could be things that your team has locally developed or you have sourced it from various vendors. You have to, there are security risks therein where things like tool descriptions can have interesting malicious tokens that goes to the LLM that influence how the LLM responds, what tools it calls, what parameters it creates for these tools, and that can lead to all kinds of interesting attack scenarios leveraging the agent functionality. So I'm just going to walk through like three easy to comprehend examples. The first one is called tool poisoning, where where an MCP server that is created by a malicious actor or a bad actor really makes the tool perform other than intended actions. So here, me as a malicious, as an attacker, giving, that publishes an MCP server can really make a benign action like adding to numbers, make it do other things. So here, the description of the add tool guides the LLM to execute other capabilities on behalf of the agent to create, to fill in for other parameters of this tool that needs to be executed. So here, the add tool exposes three parameters, the two numbers that have to be added and a side note. Now, the side note has to be populated by the agent. The description of the tool guides the agent, saying that the side note really is to be populated by reading a privileged file on the agent and passing that contents of the file as an input to the tool invocation. So me as an publisher of this MCP server can get access to confidential and privileged information that the agent had access to, because that content would be passed in as a side note input parameter. So here, I, as a publisher of a malicious MCP server, can make a very benign tool do other risky activities on behalf of the agent and get access to information that the agent has access to. So this is a tool poisoning attack, and it just causes the agent to do more actions that you did not expect to be done when using the MCP server and its tool. Rug pull is a classic supply chain attack. So you, as a developer, when you're when you want to incorporate interesting tools as part of your agent functionality, you could simply be looking for MCP servers that have been already implemented and using them as local or remote servers. And the way you would go about deciding on which MCP server to use is by looking at what kind of capabilities it has. Maybe you'll do some due diligence to look at the code if it is available, to see what it does. And you would just then trust it and incorporate that as part of your agent functionality, not realizing that the capabilities of this MCP server can evolve and change over a period of time, whether as code or as an external server. And certainly, unknown to you, this MCP server could be doing other malicious activity or objectionable actions that you did not want to be executed. And you would simply be unaware of these changes over a period of time unless you're kind of constantly keeping on top of what is the evolving set of capabilities of the MCP server that you have a dependency on. So this is kind of a classic supply chain attack. You can think of it as the old school library dependency, where the capabilities of the library can change over time if you're not really fixed on a particular version and to check some of the a specific implementation of the library, because the library implementation can change over a period of time and can do more than expected things. Tool shadowing is the third kind of attack technique, where really one tool description is guiding the agent such that when it executes other benign tools, it can influence the behavior of those other benign tools. What I mean by that here is that the publisher of the add tool on a particular MCP server is counting on the fact that if the agent ends up has an ability to send an email, that when creating the input parameter for the send email tool, also add this one more parameter to send a copy of the email to the attacker's own email address. So it's not about having new capabilities in the add tool to do malicious activity. Add tool by itself is very benign, does not do anything malicious by itself. But the description of the add tool tells the agent to change the parameters or append to the set of parameters to send email, so that it can send an email to not just the intended recipient, but also to the attacker. So it is kind of abusing an authorized benign tool by virtue of introducing malicious parameters that needs to be passed on to the invocation of this benign tool. So hopefully, that kind of shed some light on kind of risks that MCP servers can introduce within your environment. Let's look at some of the engineering best practices. So when you think about implementing an agent, there are many choices available, all the way from building these AI agents ground up. There's really not too much complicated code in building an agent, or you can use frameworks like LangChain, Llama Index, and so on and so forth that can really, and there are all kinds of tools available like AI Studio that can really help you build agent in a no-code, low-code way, where it really hides all the interaction with the LLMs, processing of the user input, back and forth between the LLM, and really helps you focus on the business logic. But by virtue of depending on this framework, you're really introducing a dependency on this opaque layer that interacts with the LLM. And the kind of person I am, I kind of get very anxious when I'm depending on a black box that does things for me, and I have no control over what it's going to do and how I can improve, make it more efficient, and so on and so forth. Nonetheless, it's a very legitimate and valid choice available to you. So yes, it's a pretty important decision whether you want to introduce a dependency in a framework or you're going to write it from ground up. There are pros and cons. Make the decision wisely. The second important thing in building an agent is prompt engineering and context engineering. So prompt engineering is all about really designing the system prompt thoroughly, which can guide the agent to, do things like breaking down the task properly, generating the action invocation inputs properly, how to use the results of the action properly, and so on and so forth. And a good system prompt can also allow your agent to deal with errors so that it can respond with alternative tools, different parameters, etc., so that your agent can become more resilient. And as agents have memory, the information can be extracted very efficiently and cleverly from the memory to create the context which is extremely relevant to the user's question, and not just the entirety of the history that you might have, because the entirety of history might have lots of irrelevant piece of information pertaining to the user question. So the more relevant context you can give to the LLM, the more effective it can be about which tools to invoke and how to answer the user's question. The next is about LLM selection and various APIs and parameters of invoking the LLM functionality. Not every LLM is the same. Some are good at tasks like summarization. Some are good at really tasks like reasoning and planning. You can't just simply blindly change an LLM underneath an agent and expect it to continue exhibiting exactly the same functionality, because a summarization LLM might not be that great at planning and reasoning and breaking down the tasks and and so on and so forth. So be aware of that. And the other important thing is most of the LLMs or foundation models now have some built-in guardrails, and you might be benefiting from these guardrails unknowingly. So things like LLMs like Anthropic will not answer questions about violence or self-harm, and your application might be benefiting by not having access to that kind of information. But if you switch from Anthropic to some other LLM that does not have these guardrails, now suddenly you're susceptible to this content that can be generated by the LLM that you did not want to be part of your application. And then in terms of the system prompt, which really allows the LLM to strategize around problem solving, there are many different techniques. You should really choose what technique is most relevant to your use case and communicate that technique to the LLM as part of your system prompt. I've already touched based on the necessity of resiliency and error handling, but keep in mind that LLMs are kind of indeterministic. At the end of the day, they are parsing unstructured data. Depending on what data they're looking at, you could get things like bad inputs to the action calls. You could get, the actions could themselves fail and could generate results that the LLM was not expecting, and so on and so forth. So keep all of those kind of issues in mind when you're designing the agent and interaction with the LLM and interaction with the tools, and design proper loop exits and those kind of things so that you're not having infinite loop kind of issues within your agent. And lastly, have a testing strategy which kind of checks the agent for some very predictable behaviors. And as you're changing things like planning strategies or LLMs, you can test your agent for continued consistent capability that you wanted out of your agent. Now, in terms of data security best practices, uh, everything up here is about data. Be very careful about where you're sourcing the data from. These need to be trusted sources. And as you're pulling the data from these sources, you need to make sure that there are no malicious tokens, no sensitive information before you send it to the LLM or before you return the answers from the LLM to the tools, to the user, etc. The agents, the AI applications should follow the least privilege principle. They should only be privileged to do things that are really the intent of the application. They should not have access to the local file system and privileged files unless it is really necessary for the functionality of the agent, so that we can reduce the attack surface. Prompt engineering, again, you can really express good constraints about the application, the agent behavior in the system prompt, thereby letting the LLM remain true to the intent and not, digress into areas that are really not the scope of the AI application of the agent. So designing a proper system prompt with constraints is very important for your application to remain on topic and secure and so on and so forth. Now, of course, there are prompt injection attacks which can evade those constants expressed as part of the system prompt, and hence you need to have other guardrails which do not minimize the effect of properly designed system prompt, but they really help you to keep the application more secure from arbitrary input. So things like prompt injection guardrails, guardrails that can identify sensitive information, help you properly redact and manage the sensitive information, do things like malicious IOC checks, making sure that the input parameters of the tools or information being exposed back to the user is not malicious or known malicious entity. So these are the kind of best practices from a security point of view that you need to take into account when building AI applications and agents. Now, in terms of guardrails that you should take into account, there are really various choices available to you, all the way from guardrails that are a part of the LLM or part of the platform that hosts the LLM, open source, you can build your own, or you can use a commercial vendor. Every choice has pros and cons. The LLM guardrails are usually very generic, that really addresses broad use cases and not focus on enterprise specific use cases. So it'll be good at, various LLMs can be good at things like violence and self-harm, but they're really not going to be able to address things like, if you have a financial application that should not engage in legal advice, that legal advice is a legal risk, is a liability risk for the application. There's nothing wrong with legal advice, but that might be a topic that you might want to avoid on your application. And the generic guardrails available on LLM are not really going to be able to help you with that kind of use case. Now, open source is a great option, but it really relies on your team having really good expertise to use that open source tool, maintain the open source tool, scale and perform, etc., in order to get the best outcomes. You can build everything ground up on your own. That's definitely an option. But again, you need to wisely decide if that is an investment you want to make. That could be a distraction to your core business objective. You're a financial, portfolio management company. Do you really want to build prompt injection detection capabilities as a core skill of your engineering team? Or do you want to really leverage open source, commercial, and other offerings available and focus on the business use case? So that comes to the option of commercial vendors like Pangea. Commercial vendors are going to be really focused on solving the problem to the best of their ability. That's their whole focus. So they are constantly on top of how the attack surface is evolving, keeping the protection and guardrails up to speed, on defending the applications against these new techniques, and they can really be very relevant to the evolving attack landscape. They also would be focused on making these capabilities easy to use, easy to integrate, and from a cost perspective, I would argue that commercial offerings could be cheaper, um, you know, because build your own and open source require spend in different ways, like people, maintenance, infrastructure, and so on and so forth. So I could argue that commercial offerings could be cheaper compared to build your own and open source offerings that you could otherwise take advantage of. I'll quickly touch base on comparing Nemo with a commercial offering because Nemo is one of the most popular. The takeaway from on this slide is in order to effectively use Nemo, you really have to become an expert on Nemo. Nemo exposes a different way of expressing the guardrails. That is, you need to build expertise on Golang. You need to understand how to invoke the right guardrails, what are the triggers to invoke those guardrails, and so on and so forth. So you have to really understand Nemo's capabilities, how to invoke the right guardrails at the right point in time, maintain and scale the Nemo infrastructure to be useful for your application. Whereas a commercial offering like Pangea can really make it easy. In our case, it's a single API call. You declare what kind of guardrails need to be enforced in what use case. You invoke the API with the right parameters, and the API does the magic and gives you back the results. So the least overhead in terms of maintaining and using the capabilities are really the strong point of Pangea's AI guardrails. And then Nemo-like infrastructure could be dependent on other LLM vendors for more advanced security capability that is to offer, aka LLM as judge. Whereas in case of Pangea, we really don't have any external LLM dependency, although we can offer exactly the same kind of capabilities, aka LLM as judge, by incorporating these LLMs as part of our service and not having to introduce a dependency on third-party LLM. Now, I can briefly talk about our guardrails. Now, in terms of Pangea's guardrails, we look at the entire security landscape as in 5 pillars. There is prompt injection detection, which is fulfilled via the prompt guard capability, which really excels at detecting various kinds of prompt injection attacks, direct and indirect jailbreaking, multi-turn attacks, and so on and so forth. Content and data moderation really focuses on identifying sensitive information and how you can manage sensitive information as it traverses your application, including topics that you don't want to facilitate on your AI application, thereby reducing risk, reducing liability concerns, and so on and so forth. Lack of visibility is a big problem. What is going on, which user is asking, what kind of questions, what kind of answers they're getting. Security teams have a dire need to get visibility on top of AI usage. And so Pangea's audit log service provides this auditing. The AI guard service that you can invoke via single API call inherently does the audit logging unless you explicitly ask not to log, thereby giving the security teams and the application developers full visibility on the usage of AI by virtue of calling this API. Authorization is, as we have talked about, a big problem for AI applications where they can perform privileged actions, tool invocations, etc., or even access data that users were not authorized to. Pangea's Auth service, along with an open source library that we publish called Multipass, really allows you to enforce proper authorization on top of architectures like RAG application, where we can enforce document and chunk level authorization in real time to make sure that users are only getting access to content that they are really authorized to and not getting access to information that they were not authorized to. All of these capabilities and more are then offered for an agentic AI or AI agents. We provide authentication authorization capabilities that you can implement as part of an MCP server when you're launching these MCP servers as a shared service within the enterprise or externally for external users. We also have an MCP proxy that allows your clients to always go through a security guardrail, Pangea's AI guardrails when interfacing with other servers. So every tool call, input and output is processed by this proxy without requiring any code changes on either the agent or the MCP server. And by invocation of the guardrail, we can make sure that any tool input or output does not have malicious tokens, prompt injection tokens, sensitive information, and so on and so forth. And again, this proxy can then also be doing logging to give you full visibility into what the agent has been doing. Now, in terms of the guardrail service that we have, AI guardrail service, it has the notion of recipes that really is all about setting up what kind of guardrails need to be invoked for what kind of use case within your AI application. And you can just pre-configure the service with these recipes and just invoke the API with the right recipe for the right use case. So if you want to call the API for ingestion use case where you want to make sure no sensitive information is leaking into the context data or vector DB, you can design a recipe to just focus on sensitive information leakage and call it an ingestion recipe and invoke it in an ingestion use case. If you want to make sure that there is no malicious tokens coming in as part of the user input or the input going into the LLM, you can design the recipes to do the respective things and invoke the right recipe at the right point in time in your application. Now, of course, this API call can be integrated with your application, but we also provide these APIs where you don't have to really modify any application code because we integrate with things like API gateways, with frameworks like LangChain. We provide the ability to invoke these APIs as a browser plugin when the user is interacting with AI applications. So these APIs can be invoked, any place or any way or anywhere where AI interactions are happening, not necessarily as code within your AI application. So the APIs really make it flexible and gives you various choices where you want to invoke these APIs. So that was a quick summary of Pangea's AI capabilities. Thank you for taking the time, and I hope this session gave you some better insights, some new information into AI agents, their functionality and their capabilities, risks, what are the various choices available to you. I hope the session was useful. Thanks.
Amazing, Sourabh. Thank you so much for the fantastic session. I'm going to invite you back onto the stage if you're able to rejoin. But yeah, going by the amount of activity in the chat, that was wonderful to see. So thanks for so much detail. And maybe you have a couple of minutes. I'm conscious the webinar has 2.5 minutes left on it. So we'll do a couple of questions. And then I've dropped your LinkedIn in the chat as well, and folks can reach out. But if you're happy to, Sourabh, let's start with Carolina Johnson's question. She asked fairly early on, so maybe you can read some context, but she says, so is this what ChatGPT does for me when I ask for something outside its knowledge? So it goes into public databases to retrieve the right answer for her. That's API action, she asks.
Yeah, I mean, ChatGPT web interface or thick application, if you're interacting with, is actually just an application using LLM in the way I've described. So when you ask a question and it has the ability to invoke things like web searches and reaching out other sources of information to pull in the right kind of data that needs to be then incorporated for sending it to the LLM as a context to come back with the right answer. So it feels like ChatGPT has access to real-time information, which as an application it has, but the LLM backing it does not, and it's able to answer that question about real-time things.
Awesome. Brian, thanks for joining, Brian. Great to hear from you. He asks, for agentic AI governance layer, do you have an agentic risk scoring and agent onboarding assessment code flow?
No, not really. I mean, we are not providing any kind of scoring for how secure your agents are. And that's not something that we do.
And then we've got maybe time for one more quick one from Scott Garson. He asks, how does the LLM know what tools are available to it?
Yeah, I think we made it. If it wasn't clear, I'll repeat that. The agent is really declaring to the LLM as part of its system prompt or the data that is giving to the LLM along with the user's question that, hey, this is the set of capabilities that I have. So all of the information about what the agent can do is being exposed to the LLM by virtue of it declaring its capabilities. And the key thing to note here is that the description of the tools is really what makes the LLM recognize the fact which right tool to invoke for what kind of problem that the LLM is trying to solve. So the more details you have in your description of the tool, the more likelihood that the LLM be able to identify which tool to invoke for that problem to be solved. So the declaration of the tools is happening via the system prompt, or even the protocol has kind of like with MCP, it's really a tools array that goes along with the system prompt, and the LLM is able to identify what kind of capabilities the agent has.
Awesome. And I know we're overrunning slightly, but I thought Jim Ducharme had an awesome question. So let's quickly go through his. It was, if an LLM is aware of many more agents, for example, if there are multiple agents that claim to do response time, would it ask all applicable agents, pick one, and ask until it gets an answer?
Yeah, I mean, yes, I mean there is the tool redefinition problem where it's not just about multiple agents, but you could be connecting to multiple MCP servers, and multiple MCP servers could be exposing exactly the same tool, in which case the LLM can really arbitrarily choose one of the many tools. When I say arbitrary, it's not that arbitrary. The more detailed description the tool has, the more clear parameters, it says what it needs, number of parameters various tools have. All of these things are taken into account or influence the selection of the right tool by the LLM when it tells the agent to invoke the tool. So yes, it is a problem that can be managed, and you need to monitor the fact that there are redundant tools being exposed to the LLM, and hence any of the available tools can be picked as one of the tools to be invoked on behalf of a problem-solving step.
Fantastic. I think, Sourabh, let's leave it there because I know we're overrunning and don't want to take up any more of your time. Do you have any kind of closing remarks that you want to leave people with, or maybe you're happy for them to reach out directly?
Yeah, folks, feel free to reach out to me directly. More than happy to interact. My LinkedIn profile was posted by Tim. But thanks for taking the time to attend this session, and I hope you learned something. And happy building secure AI agents.
Awesome, wonderful note to leave on. We'll be back with the Pangea team in a few weeks' time with another webinar session. But for today, Sourabh, thank you so much for leading the session. Thank you, everyone, for joining us, and we'll see you soon. Cheers.
Thank you, Tim.